Okay, this chapter is the collinearity and model selection. So multicollinearity. Actually, we already talked about the multicollinearity. I think it was the beginning of the multiple regression. So if we have the high correlation between the x variables, then it's gonna be a problem. It's going to be really hard to find the coefficient. Coefficient calculation may be affected by this collinearity. So you will have an unstable coefficient. So sometimes it's impossible to find the coefficient to calculate. So that's why we better not to have a high correlated two variable in our regression model. So this is a perfectly correlated situation. So I created exactly correlated. Correlation is just 100%. So as you can see, x1 increase every time, x2 increases at the same time. Whenever it's increased by 1, it's increased by 5, right? This is all same. So they are perfectly correlated. So whenever x increase, x2 also increase, and then even the size or proportion is also the same. In that case, computer has a difficulty to find the beta 1 and beta 2. The reason is when x1 is here, because this is 5 times greater, if you can change the beta 1 and beta 2, you can have infinitely many combination of the beta 1 and beta 2 that lead to the same y. Okay, so that's why we better not to have the correlated one. In this case, it's impossible, cannot be determined, because there will be infinitely many beta 1 and beta 2 combination that lead to the same y. But usually in the real world data, we will not see the exactly perfectly correlated data. But this is a less extreme case. It's not completely related. So this one is every time x1 increase, x2 also increase, but how much is increase is every time is different, right? This is just +4, right? +4. This is different. It's not perfectly different, but still it's the same. Now, as a result, beta 1 and beta 2 are very imprecise. As you can see, if we include the x1 and x2, coefficient is 84 and 2. Both of them are not significant here. But if you take it out x2, x1's effect is 95 here, as you can see. And then this is the p-value is really low. So this is significant. So when we have both of them are not significant. However, if we take it out to the x2 and x1 is significant, and you can get a similar result if you take it out x1 and x2 will be very significant. So even though it's not perfectly correlated, this is a pretty high correlation, and in that case, your coefficient you cannot trust this coefficient. Even if you change the software like Excel to the R or something else, you may have a different coefficient. No, that's a perfectly correlated case. Yes, that's why we don't want to have this high correlated two variable in our same regression model. So how can I detecting and then how can I get rid of one of them? So we can create a correlation matrix, and then you can find out which variable and which variable has a high correlation. But there is one specific measure, which is a variance inflation factor, right? And then if the VIF is greater than 5, then we say multicollinearity exists. So this one is just measuring one variable against all the other variable. So we cannot tell this variable has a high correlation with with which one. We cannot tell which one. But we can tell this variable can be can have a pretty high correlation with the other variable. So here this is xi is the, if you take it out the r square j without j, okay? So this is the r square is the r square regression result of r square without j's variable, okay? Yeah, and then you don't have to calculate all of this case, and then we can use R, and then you can find out the VIF. Okay, so if we find out the greater than 5 VIF, then what you have to do is you better have a more sample data, so that hopefully the new data weaken the correlation, or if you can just taking out the correlated X variable. So how can I get a VIP in the R is this way. You can get a wage data from the package here, and then you can see the what is the wage, and then we call the library, the car library, the regression, and then you do the regression here, and then if you just simply use a function VIF, and then put this regression model here, and then you can see the VIF value for the each variable. So here, as you can see, this all the 1 point something, 1 point something. So we can say there is no variable has a high correlation with other variable. So yeah, we don't have to worry about the multicollinearity here. So once you find out the one value, one variable that has the greater than 5 VIF value, then maybe you have to consider the taking out that variable. So here this is not the 5, but what if the tenure got like 8 point something something something, which means this tenure can have a high correlation with others. I don't know with which one, or combined together. So sometimes this is like that. We have a variable a, b, c, but c is same as a plus b, right? So c is not perfectly correlated with a, c is not perfectly correlated with b, but c is perfect, actually the same value as a plus b. In that case, you will have a pretty high correlation here. VIP will be really high. Okay, that's what it means. VIP is high means this variable C is high correlated with other variable. It doesn't tell you which one. Maybe it's not the individual one. It might be the combined one, just like this. So you may take out the C. You have to consider the taking out the high VIF variable. Residual analysis. Residual is the difference between your regression model result and then the real data. That's the residual. Because that's the part of the actually here, right? This is the residual part. Our model captured something, but actually our model is not perfectly fit our data, which means there is something we are missing. That's the residual. So using the residual analysis, we can evaluate is there any violation of assumption. Our linear regression assumption has a normality, so our residual should be the normally random. Normal random means, yeah, we don't know what is the factor, important factor, but we can consider that what we don't know can be just random noise. If it's not normal, then yeah, there's something important we are missing. We have to figure it out. But the residual is normally distributed, then we can consider that's just a random noise. So the error residual should be the normality. Constant variance is the variance is everywhere. That should be the same variance. If it's not, then there's something going on. And independence of the error. Actually, this is usually for the time series data. So we will go over the time series. We will see in the next chapter. Normality. Examine whether or not the observation, which is the residuals, are from the normal population. So the residuals are the normal population. So how can I check this one? Is a normal probability plot. So normal probability plot will give you some dots, right? And then your dot might looks like this. Depends on the how off your dot is from this line. If you ideally all the residual dot is perfectly fit onto the line, then this is a perfectly normal distribution. But no, we cannot get a that's perfectly normal distribution. But if all the dot lines are close to the straight line, then you say you will be fine. How can I draw this one? Is using the QQ line function. So usually it's a QQ line, and then you can put the residual. How can I get a residual? It's just there is a function for the residual. And then you put the linear regression model we use, right? And you put this one into here, then you can collect only the residual values. And then putting this residual into here, then QQ line will give you this normal probability plots. Constant variance. This is we already discussed. This homoscedasticity. Actually, I still have a problem to pronounce. So hetero here, the hetero means it's different, right? And the homo means it's the same. So everywhere it's a similar variance, but here the variance is moving, getting bigger as x is getting bigger. So we won't have this assumption, but if we have this assumption, you may have to change something. That's why we may have apply the log things or something else and to resolve this problem. So you can check is it our linear regression model doesn't violate any assumption here. Then you can see it using residual plots. Independence of error is we call it autocorrelation. Autocorrelation is correlation with itself. So this is a minus. So minus. This is plus, 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 minus, minus. So there is a high probability the sign of your value is high probability that will be the same as your previous value. So if it was this are not always true, but high probability. Once this is positive, you can have a positive, and next is positive, next is positive, and next is positive. This is a violation, plus to the minus, but minus to the minus is not violation. So there's only 2 points it violated that rule. If previous one is minus, I tend to have a minus. If previous one was a positive, I tend to have a positive. So that's what we call this positive correlation. Only 2 points there's the error, the violation of the perfect autocorrelation. In this case, it's totally opposite, right? Previous one is minus. Next, now I want to have a positive. This previous one was positive. I want to have a negative. Plus, minus, plus, right? Minus, plus, minus. This is there's no exception every time it happens. Previous one is minus. Next one is positive. Previous one is positive, next one is negative, right? So that's why we call this a negative autocorrelation. This is makes sense if our data points has some kind of order, right? If we can mix up to the order, if we say like the data about our customer doesn't have an order, right? So this autocorrelation or independent of error is important in the time series data when there is the sequence. right? Or order. There's no first one or second one. If we collected just this is a collection of our customer, or a collection of all the countries, some economical numbers, there's no order. Then we cannot talk about the autocorrelation here. So there is a kind of test if we really have an independence of error or not, or is there the autocorrelation or not. That's the Durbin-Watson test, but we will talk about it when we talk about the regression with the time series data, because again, this is important when we have a time series data, sequenced order. But most of the data so far we use is like trying to find out the job training effect. So we collected all the employee information. There is no order of the employees, right? So in that case, we cannot talk about the autocorrelation at all. So I will skip this part. I will not go deeper about autocorrelation here. But it will come in the regression with the time series data.